Physics, like all other live sciences, is in a constant state of change. However, some changes prove to be more significant than others. The first big change occurred when Newton revolutionized the physics of ancient Greece. Whereas the Greeks believed that objects in movement tended to stop, Newton stated that objects tend to maintain their previous motion state if no net force is applied. The most important change in the history of physics was of course the change from classical physics, namely Newtonian physics, to modern physics, relativity and quantum mechanics. This change is based, amongst other things, on an experiment conducted at the end of the 19th century, known as the Michelson-Morley experiment. Recently, due to an incompatibility between relativity and quantum mechanics, scientists have been pushing towards another change, finding a so-called theory of everything, and perhaps it will be another key experiment that will bring this change to fruition. Of course, all physics involves a few basic concepts, such as space, dimensions, time, and energy, which may entail gravity, electromagnetic energy, mass, and kinetic energy. Going back to the 19th century, scientists knew that sound travelled as a wave, using air particles that transmit vibrations. They knew that light also travelled as a wave, as light can reflect, refract, and interfere with itself. However, the fact that light could travel through a vacuum puzzled them for many years, until they proposed a new material, the luminiferous ether, a substance that cannot be seen or felt, but that fills the universe and allows the propagation of light. In 1887, Michelson and Morley carried out their experiment in order to attempt to prove the existence of this luminiferous ether. They tried to measure the speed of the Earth through this ether. They hypothesized that if the speed of light was measured during the winter, it would be different from the speed measured in the summer, as the Earth would be travelling in the opposite direction from the ether. Perhaps it would be best not to mention the rotation of the Earth, we might get dizzy. However, they found that there was no difference whatsoever in the speed of light, no matter where it was measured, and this paved the way for Einstein's special relativity, which would take the speed of light as a fundamental constant of the universe. So, in this search for a new theory of everything, there is one experiment that may possibly be the key, an experiment designed to detect gravitational waves, which has been a goal of scientists ever since relativity was first proposed. The LISA, Laser Interferometer Space Antenna experiment, which will be conducted by NASA in the following years. Unfortunately, it has already been postponed various times. It consists of an interferometer in space which will be able to detect gravitational waves, given the impressive precision achieved by having the space shuttles be very far away from one another. LISA has been labelled as essentially a giant Michelson interferometer in space. However, they could be in for a big surprise. Instead of LISA detecting gravitational waves, it could be that the interferometer behaves as the classics thought it would in the original Michelson-Morley experiment. This experiment could therefore provide an alternative explanation to relativity, which hopefully would not entail the curvature of space or the dilation of time. The new approach could mean the existence of a mobile ether, known also as the gravitational field. After all, it is feasible that electromagnetic energy has no direct physical support, but a medium support of another energy field within a physical support of a three-dimensional grid of unbreakable filaments.